Hello, everyone. I want to first thank you all for attending the presentation. As part of the Netzsch Polymer division, we have been working with John and Professor Tim Oswald at the Polymer Engineering Center for many years now, and they've accomplished some very impressive research. This webinar is only a small snapshot of their results. I think you may see that John might have the record for the person with the most hours logged on Netzsch instruments for the past year. But I won't take any more of your time, and I'm happy to pass the presentation over to John so he can share some of his work.
Thank you very much, Deborah and Alec, for the warm welcome. Good morning, everybody. My name is John Emanuel Estela-García. I am a graduate researcher with the Polymer Engineering Center under the supervision of Dr. Tim Oswald. And I'll be presenting today the role of material characterization in polymer manufacturing, where we're going to be addressing the impact and challenges of recycled material. So when we're discussing the challenges regarding plastic recycling, it's relevant to understand the scope of plastic use, including what would be projected growth in terms of production, consumption, and waste generated. We can start by analyzing this graph showing the market sector allocation for commodity plastics. Notice the significant portion occupied mainly by polyolefins, especially polypropylene, low-density polyethylene, and high-density polyethylene. Their prevalence is very high in packaging, noted by this light blue bar, and their height highlights their dominance across various industries. This widespread use underscores the versatility of plastics, but it also hints at the scale of the waste challenge that we face. The prevalence of plastics, particularly in our daily lives and across industries, is not a coincidence. It is the versatility that has led to their adoption in everything from packaging to construction to consumer products to medical devices and electronics. This widespread use stems from several key advantages. Plastics are inexpensive, they're widely available, they offer good mechanical properties and strong chemical resistance, and these benefits have driven their integration into countless applications. So now we can turn our attention to this graph, which is highlighting the projected plastic use in the United States. This trend is very clear and a little bit concerning. Across the following years, we're expected to see a surge in plastic use. And this surge is approximately 90%. So from here on out to 4 decades, a 90% surge in plastic use. And this projection raises some concerns, particularly in the environmental impact, such as how we're going to be dealing with this plastic waste. So this allows us to start considering the challenges with current waste management techniques. So while the plastic industry contributes significantly to the global economy, it finds itself at a crossroads. The economic benefits are clear, but there are challenges that are related to sustainability and waste management. So there's a sort of tension between the economic value and the environmental concern. So that's going to be key in our discussion on sustainable polymer manufacturing. So there are some unsavory truths about our current plastic waste management practices that highlight our urgent need for innovative solutions. We can start by examining this graph where we're showcasing different trends in plastic waste disposal in the US across 3 decades. The most striking feature is the dramatic increase in landfilling. Incineration has seen a modest increase, not as much as compared to landfilling. And recycling, while it has some growth, it does remain disappointingly low. So despite the awareness and demand for recyclable materials, only 9% of plastic waste is actually recycled in the US. This low rate persists even for materials that are considered easily recyclable. And this kind of points towards systemic issues in our recycling infrastructure and the processes that we utilize. The consequences of these low recycling rates is 75% of plastic waste in the US ends up in landfill. This not only represents a significant waste of resources, but it contributes to long-term environmental issues. So we can break down, I think it's important to consider the breakdown and the composition of waste. If we start separating the waste by polymer type, this pie chart here is showing us that polyolefins, again, HDPE, LDPE, and polypropylene together make up 70% of the plastic waste that we're seeing. This aligns with what we saw earlier regarding the prevalence of polyolefins across various sectors. When we separate waste by application, we start seeing packaging dominate with 37% of plastic waste. The second largest one would be right here, consumer and institutional products. So together, plastic packaging and consumer products is already 50% of plastic waste. It's worth noting again that the packaging sector is dominated by polyolefins. So this again explains their high representation in the waste streams. So single-use plastics represent a large portion of US plastic waste. So we're facing a critical situation. Despite the recyclability of plastics, our current systems fail to capitalize on the potential of them. The vast majority of plastic waste continues to end up in landfills, and this creates a significant environmental burden. It's important that we consider the economics of such practices. So although landfilling is our major route for plastic waste, we are literally burying billions of dollars in valuable resources. So these are just the enormous economic and environmental costs that come with the current plastic waste management practices. We can start by examining this bar graph here that is showing the fate of different plastic types in our municipal solid waste stream. So for most plastic types, nearly 90% of them end up in landfills. Only a small fraction of them are actually recycled or combusted for energy recovery. And this graph starkly illustrates the massive opportunity we're missing in terms of resource recovery and circular economy principles. So we can actually put a dollar value on this missed opportunity. So this table right here shows the average market value of landfill plastics. And the numbers are pretty staggering. HDPE, LDPE, PP, and PET together represent billions of dollars of value just literally buried each year. So when we total up all of these landfill plastics, the estimated average market value reaches an astounding $7.2 billion annually. And this isn't just an environmental tragedy. You can consider that an economic tragedy as well. Landfill plastics leads to a lost market value. That's $7.2 billion. But it also represents a significant economic opportunity. By diverting this plastic from landfills, we can recapture value, reduce environmental impact, and drive innovation in sustainable manufacturing practices. So we turn our attention to a critical area of waste plastic management. Particularly in this infographic, we are depicting a material recovery facility, or a MRF. So what we are observing here is the flow of materials through a MRF. These facilities are the forefront of our efforts when it comes to sorting and recycling plastic waste. Many capable of even handling both post-consumer and some post-industrial plastic streams. So MRFs receive a diverse input. They include flexible plastic films, textiles, municipal solid waste. They recover some low-value products, such as glass, cardboard, and metals, while materials that can't be recovered are sent to landfills, either for combustion or gasification, or just storing in the landfill. It is important to note that most MRFs are funded at the local government level, which limits the materials and capacities that a MRF can actually process. So traditionally, most MRFs have their sorted plastic sent for material recycling through extrusion. However, this often results in resins with degraded properties, as the quality of their sorting is limited by the sorting equipment and capabilities found at the MRF. This is where new advanced recycling methods come into play. For instance, dissolution-based approaches allow for the recovery of pure resins from complex feedstocks. Pyrolysis allows for catalytic upgrading or steam cracking, and these advanced methods represent a significant leap forward in our ability to recycle plastics effectively and maintain a material quality. So let's contrast these promising technologies with the reality of our current recycling efforts. So this graph shows the stark disparity between plastic waste generation and plastic waste recycling rates in the US. So while plastic waste generation has increased dramatically, our recycling rates, again, are abysmally low at around 10%. This gap underscores the need for advanced recycling methods. The challenges we face are clear. There are stagnant recycling rates in the face of increasing plastic production, consumption, and waste generation. And our current infrastructure is just not keeping up pace with the volume of plastic that enters the waste stream. So new technologies, like advanced recycling methods we discussed earlier, do offer a path forward. But it is equally important to establish MRFs, because those are going to be the forefront, and they're going to be crucial in developing an enhanced industry for plastic reclamation. So we face the critical challenge of effectively managing and recycling an enormous volume of plastic waste that we generate. But we also have to attempt to balance our demand for polymer resin. This illustration here is showcasing the complex web of plastic management from production to end of life. And we see 4 key stages. We have the monomer producers, where techniques like thermal depolarization and solvolysis break down plastics to their basic building blocks, which can then be used to produce virgin grade polymers. We have the product producers, where methods such as dissolution and mechanical recycling maintain some of the polymer structure for reuse into end products. We have waste sorting, which is the crucial step that impacts the quality and quantity of recyclable material. And then we have our end of life processes. And while incineration and landfilling are still common, the goal is to minimize these over time. And these interconnected techniques create essential recycling loops, pointing towards a more circular economy in plastic production and use. So we can turn our attention to predicted polymer demand. These projections on the right are both challenging but promising. Here in 2020, we see that there was a demand of 350 million metric tons for plastics, with only about 7% of that being supplied by mechanically recycled materials. Fast forwarding to 2030, we're looking at a demand increase to 500 million tons. Recycled content is projected to increase significantly, tied together with advanced recycling. This could contribute to 20% of the demand. However, this still leaves 80% still coming from virgin materials. What's particularly striking is the investment that is required to achieve these goals. It's estimated $40 billion in investment into advanced recycling would be required by 2030. And by 2040, with an increased projected growth of 700 million metric tons per year, we're looking at a staggering $90 billion in investment in advanced recycling. So these figures underscore the massive opportunity and necessity for innovation and investment in recycling technologies. And these developments in waste plastic management, they're not just technical challenges, but they require a reimagining of our relationship with plastics. There has to be a shift from focus on products that are made to be recycled. So we can look at how some of these recycling techniques tackle one of the biggest problems, flexible packaging. Packaging is a major source of single-use plastic waste and presents unique challenges in recycling. From the inks and the adhesives that are used to the presence of multiple layers of different plastics, there's a lot that goes into recycling some of these materials. So right on the left, I'm showcasing an infographic that's demonstrating the mechanical recycling process for pure LDPE films. This is something that you could expect to be occurring at a MRF. So it's a multi-step journey. It starts with the recovery and sorting that occurs at a material recovery facility. There's the shredding steps and washing steps and drying steps that are required in order to clean the material as much as possible to prevent any contamination, or at least most of the contamination. Right once you have the material dried, it is then fed to an extruder where it can be pelletized before being recast into a film. While this method is well established and used, it does face limitations in handling contaminated or mixed plastics, and this often results in degraded properties. Now we can look at an advanced recycling method. This method is called solvent-targeted recovery and precipitation, STRAP. So this process focuses on using specific solvents to target polymers in mixed plastic waste. So we have here a as-received plastic waste that is being fed into a dissolution tank with a specific solvent that is targeting one plastic in that material. So the plastic that is being targeted becomes dissolves inside of the solvent, which can then be precipitated outside. So the non-dissolved pieces can then be fed into another dissolution chamber to recover another specific plastic. This allows us to achieve higher purity in recovered polymers, but it does involve dissolution, precipitation, and solvent recovery steps. STRAP is capable of handling more complex waste streams and potentially yielding this higher quality recycled materials that are required for our polymer products. This final infographic demonstrates STRAP in action. We've been able to showcase this. We have here post-industrial multi-layer printed plastic film. After being subjected to STRAP, we have recovered the polyethylene components. We were able to then extrude and pelletize this recovered PE and then produce a 100% recycled polyethylene film at the factory. So this real-world application showcases the potential of advanced recycling in creating high-quality materials. So sustainable polymer manufacturing faces significant challenges in recycling technologies and recycling utilization. These challenges span both technical, economic, and even regulatory domains. As discussed, there are various recycling methods, and each has distinct challenges, pros, and cons. Mechanical recycling offers cost effectiveness for pure streams, but struggles with contamination and quality degradation over multiple cycles. Dissolution preserves polymer chain length and removes additives, but it faces hurdles when it comes to solvent recovery, material compatibility, and the cost of implementation. Landfilling, while presenting low immediate costs, they do incur long-term liabilities and even the squandering of valuable resources. The diversity of these methods just reflects the complexity of our recycling challenges, and there's not a single approach that provides a comprehensive solution. There's not a silver bullet to the plastic waste problem. A key manufacturing issue in recycling is particularly material variability, and this directly impacts crucial material properties. Overall product consistency becomes difficult to maintain, and these property variations pose significant hurdles for manufacturers that aim to incorporate recycled material consistently and reliably. My apologies. The economic landscape of recycling is also complex. Price volatility between recycled and virgin materials, substantial capital investment requirements for advanced processing, and then the shifting market dynamics due to evolving regulations, corporate policies. All of these will impact the viability of recycling initiatives. Despite all of these challenges, there are several factors that are driving innovation in recycling technologies. There are ambitious sustainability targets, there are growing consumer demand for eco-friendly products, and then there's evolving regulatory policies. And these drivers are an integrated approach that is required to increase recycling. So with the background already laid, we can start talking about the need for comprehensive material characterization. And this need stems from the complexity of recycled materials and the impact that they can have on manufacturing. Recycled materials stem from diverse sources. They include various polymer types, grades, and qualities. Post-consumer recycled plastics, they've undergone a use cycle, so they differ markedly from post-industrial recycled plastics in composition and properties. This variability extends to contamination issues, including contaminants like paper and cardboard, to cross-polymer contaminants like polypropylene and PE streams. Recycled polymers can contain legacy stabilizers, pigments, plasticizers, while previous processing and use cycles lead to chain scission and oxidation, which can form degradation products. These factors collectively alter thermal stability, mechanical properties, and overall material behavior. This impact on manufacturing, one moment. This impact on manufacturing processes is substantial. The inconsistent flow behavior can affect extrusion and molding processes. It can lead to increased equipment wear and contamination buildup, and then you end up with product quality issues that result in failure to meet mechanical property specifications. The economic ramifications include elevated scrap rates, extended production downtime, and potential customer dissatisfaction. To address these challenges, it is crucial to bridge material science and manufacturing through aligned testing methodologies. This approach involves selecting tests that are going to provide actionable data for manufacturing decisions and implementing these protocols that ensure data comparability across production runs and facilities. We have to be able to compare what we're measuring. We have to be able to use these values adequately. And this comprehensive material characterization does offer several benefits. You have a proactive quality control and assurance. You can optimize your processes through every manufacturing stage. And continuous improvement is driven by having an informed feedback loop, utilizing actionable data. So we'll take a moment to look at some of the characterization tools that are at disposal. We'll start with thermal analysis. Thermal analysis provides valuable insights into polymer behavior. When we're examining heat flow, we can pinpoint critical temperatures and transitions that dictate processing conditions and end-of-use performance. This is especially useful when you're working with recycled feedstocks, where variability and contaminants can pose challenges. Crystallization kinetics, for example, they influence everything from the processing speeds to the final product properties. So understanding these kinetics becomes critical when comparing virgin and recycled materials. So as we aim to minimize changes to processing parameters and product quality, DSC is a crucial tool for this. Thermal stability is another cornerstone for polymer characterization. It's not just about knowing when a material breaks down, it's about understanding the mechanisms behind it, what pushes this degradation to occur. And this knowledge is useful for predicting long-term and high temperature performance. Moving on to flow properties, we focus on rheology. The behavior of molten polymers during processing can make or break a manufacturing operation. When working with recycled materials, these properties can vary significantly. So this requires a deeper understanding to maintain consistent quality. Mechanical testing rounds out our toolkit. It provides crucial data on how a material will perform under stress or strain. And as we incorporate more recycled content, we have to maintain the mechanical integrity. So this becomes a delicate balancing act that relies heavily on all of these characterization techniques. And it's important to not overlook the importance of molecular structure. High temperature gel permeation chromatography provides insights that are crucial for predicting mechanical and flow properties. And they're useful when you're deciding how do we incorporate recycled materials to the production line. All of these characterization methods form the backbone of our efforts to create more sustainable polymer products. They allow us to understand, predict, and control the properties of our materials. So we're going to start by exploring two key types of recycled materials: post-industrial recyclate and post-consumer recyclate, PIR and PCR. These materials represent different stages in the plastic life cycle, and both bring unique challenges and opportunities for our industry. We're going to begin with PIR. This material comes from the manufacturing process itself. You can think of scraps, cutoffs, rejects that simply never make it to the consumer. PIR is often cleaner, more consistent than its post-consumer counterpart, and it hasn't been exposed to the wear and tear of consumer use, nor the potential of contamination that comes with it. So this relative purity makes PIR an attractive option for manufacturers that are looking to incorporate recycled content without significantly altering their processes. However, PCR is an entirely different story. This material has already completed its journey through consumer use and disposal, and a good way to put it is it's simply been through the ringer. PCR can vary widely in composition and quality. It depends on the source and the efficiency of the recycling process. It may contain different plastic mixes, additives, even non-plastic contaminants, and the viability is both a challenge and an opportunity. The key difference between PIR and PCR is their history. PIR has a known pedigree. We understand its composition and processing history. PCR is a mystery box, so it's going to require more rigorous testing and sometimes more sophisticated processing approaches to bring it up to manufacturing standards. In the context of sustainable manufacturing, both PIR and PCR play crucial roles. PIR represents an opportunity to close the loop within manufacturing, reducing waste and improving efficiency, while PCR, more challenging to work with, is essential for creating a truly circular economy for plastics. It's about taking responsibility for the entire life cycle of our products. The goal at the end is to increase our use of both types of recyclates. This means developing new technologies to better sort and process PCR and optimize our manufacturing processes to accommodate a higher percentage of recycled content. Again, this is a balancing act between maintaining product quality while also increasing sustainability. So when we're discussing sustainable polymer manufacturing, we're not just looking at how we recycle materials, but how we can do it in a way that maintains the integrity and quality of the polymer through multiple reprocessing cycles. So here we have an experimental setup that's mimicking real world conditions. We are pushing polypropylene through multiple extrusion events, mimicking PIR. This approach allows us to see how the material changes over time, giving us insights into the longevity and recyclability of the polymer. So we use different processing conditions where we can gauge the impact of specific variables on the stability of the material's properties. Each pass through the extruder leaves its mark, and we can see this unfold right here in this image, where we can appreciate the changing appearance of our samples as they are continuously exposed to the same extrusion conditions over and over and over and over again. So temperature is our first variable. It's not just about melting the polymer. It's about finding the spot where we can process the material effectively without causing unnecessary degradation. It's too hot, we risk breaking down the polymer chains. It's too cool, we may not achieve proper mixing and homogenization. Then we have screw speed. It's not just about how fast we can push the material through the equipment. The screw speed affects how well the polymer melts, how thoroughly it mixes, how much shear stress the material experiences, and all of these factors play into the final properties of our recycled material. Finally, residence time ties it all together. I'm a chemical engineer, so I'm looking at the extruder essentially as a chamber, a reaction chamber. And residence time is telling us how long is the polymer exposed in this high stress, high temperature environment. So this is a balancing act. We need enough time for proper melting and mixing, but not so much that we start seeing significant degradation. So why does this matter? In the world of sustainable manufacturing, it's not enough to just recycle materials. We need to recycle them in a way that maintains their performance characteristics. Every time we put a polymer through this process, we want it to come out the other side ready to perform just as well as it did the first time. And no matter what type of process you're doing, chances are how you recover your polymer, it will still end up going through an extruder. We need pellets. It's easier to work with in many instances. So by understanding and controlling these parameters, we're not just recycling, we're optimizing our process. We're finding ways to process materials that minimize degradation and maximize our performance. So not just about reducing waste, but creating an economy where plastic materials can be reused again and again and again with minimal loss to their essential properties. So we turn here to a critical parameter, residence time. This factor plays a pivotal role in determining the final properties of our recycled materials. So we've here employed a colorimetric approach to visualize and quantify residence time. So there we go. By analyzing our data, we see some intriguing trends depending on our processing conditions. There's different residence times depending on the heat and screw speed that is being applied. So residence time and its distribution, what we're observing here, are key determinants of product properties and extrusion process. They influence the degree of mixing, the extent of reactions, and ultimately the quality of our final product. In mechanical recycling, we can model continuous reprocessing events as increases in residence time. This approach allows us to draw direct connections between processing time and property degradation. By fine-tuning residence time, we can potentially extend the number of times a material can be recycled without significant loss of properties. So let's kind of focus on some of the experimental methods that we're applying. We have a suite of analytical techniques to evaluate the material's property across multiple processing events. We began with mechanical testing, where we're utilizing tensile tests to determine the modulus of all samples. To ensure consistency, we injection molded samples into dog bone shapes. This approach allows us to track changes in mechanical properties as the material undergoes repeated processing. For full property analysis, we conducted melt flow index tests on pelletized samples. We then compression molded these pellets into disc for rheological characterization. And again, we maintained consistent conditions for the molding to minimize variability in our results. Lastly, we performed thermogravimetric analysis, or TGA, to assess thermal stability. This method provides insights into material stability changes between processing runs and allows us to construct degradation kinetics models. So by combining mechanical, rheological, and thermal analyses, we gain a holistic view of how PIR behaves under repeated processing conditions. This approach is crucial for developing sustainable manufacturing practices, and it allows us to identify the limits of material recyclability and optimize our processing parameters. So let's start this little video here. What we're observing is two samples of recycled PIR dog bones, where one of them is undergoing strain hardening on the right, and the other one undergoes break on the left. So the tensile modulus data across multiple processing events is marked here. And what we can observe is the relative stability in mechanical performance, but while also understanding that the stability compared to the original values, it has been changed by the processing conditions, the extrusion conditions of this recycled PIR. So we observed that lower temperatures in extrusion can lead to increased stiffness in our recycled material. And this finding has important implications for recycling processes when it comes to maintaining or modifying mechanical properties. The predictable nature of these property changes is valuable for manufacturers. It allows us for more accurate forecasting when it comes to material performance over multiple recycling cycles, potentially extending the usable life of a polymer. So these results suggest that with careful control of processing conditions, we can maintain consistent mechanical performance in recycled polypropylene specifically. The stability in mechanical properties is a key factor in promoting the use of recycled materials in high performance application. This is providing manufacturers with the confidence to incorporate higher percentages of recycled content without compromising product integrity, focusing more so on the conditions that you're processing your material at. There we go. The analysis of melt flow indexing in relation to the cumulative residence time reveals insights into polymer degradation during recycling processes. When we correlate MFI with our cumulative residence time, we've developed a more nuanced understanding of how processing conditions impact material properties over the repeated life cycles. So we're linking flow properties to exposure to heat and stress over time. And our data shows distinct trends for different processing conditions. Notably, higher temperature conditions exhibit similar behavior. We can see that by how the purple and green lines and the blue and red lines start having similar behavior. More notably on our data over here on the right, showcasing the molecular weight changes. So this suggests that temperature is a dominant factor in polypropylene degradation during extrusion. So by understanding the relationship between processing conditions and polymer degradation, we can optimize recycling processes to maintain material properties over multiple use cycles. So this is essential for extending the lifespan of plastic materials. We've validated some of our MFI results by comparing them with gel permeation chromatography measurements of molecular weight. So the correlation between these methods demonstrates that MFI testing can provide quick, reliable results comparable to more complex analytical techniques. It has high test reproducibility, good agreement with the gel permeation chromatography results, and it allows the manufacturer clear evidence of what is the impact factors that affect their final properties. So we can now focus on rheology. So when we performed rheology, we had mentioned that we made these little discs. We compression molded these discs. We utilized cone and plate, steady shear, and oscillatory rheometry to capture changes in viscosity and shear effects. So these results were utilized to construct viscosity curves, but the data shown here is simply focusing on the zero shear viscosity captured from the Newtonian plateau. When we compare these results to MFI, there are in fact higher variabilities in the rheometry results, but these variations could simply caused by the innate sensitivity of this test to the polymer architecture or the sample preparation method. Nonetheless, we do see similar trends as appreciated by the MFI testing. Rheometry was very useful in constructing viscosity curves that allow us to compare the entire flow behavior and contrast it against recycled materials to determine if we can match the same flow qualities. This allows us to minimize process parameter changes required to process recycled feedstock. Results can also be used to quickly determine if the material is suitable for specific processes. So moving on to thermal stability, thermogravimetric analysis is a critical tool in understanding polymer behavior under thermal stress. It provides essential insights into both thermal and even thermal oxidative degradation processes. In polymer manufacturing, TGA in an inert environment reveals pure thermal degradation characteristics. However, the real world involves oxygen, making thermal oxidative degradation also relevant. Oxygen will lower the activation energy for chain scission, which accelerates degradation. So the applications for TGA are extensive. You can use it to determine critical degradation temperatures. You can use it to evaluate kinetic parameters. You can use it to assess the impact of processing on your material stability. You can use it to determine how the material degrades over time and predicting that. The comparison between inert and oxidative atmospheres allows us to reveal stability differences, which is invaluable when you're trying to determine what material to utilize and how to optimize your process. And this particular knowledge is useful when you're trying to compare the thermal history of recycled materials, where the history that the recycled material has gone impacts the material properties. So on this slide, we can appreciate the comparison between the thermograms of polypropylene subjected to an inert environment and an oxidative environment at two different heating rates. It's important to note that for the oxygenated environment, we utilize 10% oxygen. This is taking the assumption that oxygen has poor permeability throughout the polymer melt. We have three separate mass loss changes that are detailed: 5%, 50%, and 95%. These three steps are particularly useful, especially the 5% one, because it helps avoid issues where volatiles exuding from the polymer can be mistaken as polymer degradation. The presence of oxygen has a massive effect on thermal stability of the polymer. We can see that when we're comparing these slopes. It reduces the thermal stability of the material by up to 140 degrees in this case. For the inert environment, we're observing a single slope, which is characteristic of polypropylene and other polyolefins during pyrolysis, is simply detailing chain scission. When we observe the oxidative environment curves, we can see that there's a slower heating rate. There's a secondary slope. That means that there's a different reaction occurring, but we can't really appreciate that at the higher speed the second slope is not readily apparent. So this indicates that this is a slow reaction that can't be observed at higher heating rates. So this is now detailing the importance of adequate standardization of testing procedures. In this slide here, we're observing the results of TGA of the virgin material compared to various final extrusion conditions, with respect to both nitrogen and an oxidative environment. So when we're comparing the results of the thermograms, we can see how the stability of the polymer is affected by the testing environment. For the inert condition, we appreciate that for all the samples, no matter if they've been extruded multiple times, regardless of their extrusion conditions, they demonstrate the same degradation behavior. We're just seeing one singular slope. When we observe the TGA thermograms for the oxidative results, we observe varying behavior between samples. So this is alluding to differences in the degradation mechanisms and in the polymer stability. So these subtle differences can be investigated through kinetic analysis approaches. And these analyses can yield forecasting tools for polymer degradation. And these can then be used to determine optimal temperatures to minimize degradation during processing or maximize degradation during pyrolysis. On this slide, we appreciate the TGA results of the virgin polymer with various heating rates with respect to both the inert on the left and oxidative environment on the right. When we're comparing the results of the thermograms, this allows us to observe the stability of the polymer being heating rate dependent. So due to a polymer's poor thermal conductivity, higher heating rates create larger temperature differences within the material. And this shifts the thermogram to the right. When we're focusing on the oxidative data, we can again appreciate this secondary reaction during the slower heating rates. And once we reach 10 Kelvin, we no longer appreciate this. So the basis of a good kinetic analysis is having ample data at varying heating rates, which allows us to capture significant degradation events and thermal dependencies. We can also here appreciate how this looks like. So with the data demonstrated before, particularly the virgin one, we're going to employ two distinct approaches to kinetic analysis. We're going to apply the Redmann method, and then we're going to apply a model-based approach. The Redmann method is widely used for polyolefins. It calculates the activation energy of a reaction as a function of conversion degree. And this approach is particularly valuable for simple systems and is very much prevalent in pyrolysis modeling. In contrast, the model-based approach is more suited for complex multiple-step reactions, such as what we would observe in thermo-oxidative processes. It considers individual reaction steps, describing them with a system of kinetic equations. With these tools, we can then describe kinetic mechanisms and observe how reprocessing affects these mechanisms. Careful testing allows us for studying the impact of reprocessing and degradation on reaction kinetics. And the choice between method depends on the complexity of the system that we're studying. Each method has its strengths and limitations, and their combined use often provides a more comprehensive understanding of polymer degradation kinetics. So we'll focus our application on the virgin polypropylene as a benchmark and demonstration. So the Redmann analysis of polypropylene degradation in an inert environment reveals insights into the polymer's thermal stability. The Redmann analysis is performed by plotting the natural logarithm of the change in conversion against the inverse temperature over the entire range of conversion. And the slope that we observe here, these are called isoconversional lines. And the slope of these isoconversional lines leads us to calculating activation energy. By examining the activation energy across the conversion range, we observe three distinct regions. We see a low activation energy region, and this corresponds to the breakdown of weak points in the polymer structure, such as chain ends, branch points, regions that have structural defects. And these weak points require less energy to initiate decision, making them the first to degrade during thermal stress. By following this, we observe a region of relatively constant activation energy. This represents a systematic unzipping of the polymer backbone. So this is what we refer to as that main chain scission. This stage involves the breakdown of the primary polymer chains. And finally, we encounter this high activation energy region, and this corresponds to the scission of the most stable polymer parts, the most stable polymer chains, lower molecular weight species that remain after this. So as degradation progresses, the activation energy increases because the remaining material consists of simply more thermally stable structures. It's crucial to note that recycling processes can alter this profile simply by introducing new weak points or changing the distribution of chain lengths in your system. In our kinetic analysis of polypropylene degradation in a 10% oxygen environment, the Redmann method fails to provide consistent results across different heating rates, particularly as we're approaching complete conversion. And this is simply due to the complexity of the reactions that take place. The presence of oxygen facilitates controlled depolymerization through the formation of peroxide and radical species. And these reactive intermediates significantly lower the activation energy that is required to break down the polymer. While this complicates the kinetic modeling, it provides valuable bounds for determining kinetic parameters. This range of values is crucial in developing an understanding of polypropylene degradation. So due to the knowledge of the reaction step and mechanism, a simple one-step reaction model is created for the inert environment. And this gives good agreement with literature values. It matches our data well. This allows us to model something like pyrolysis utilizing this material. And the current model that best captures the oxygen environment data actually consists of 6 reaction steps. And the model is based on the assumption that the thermal oxidative degradation of polypropylene occurs with a change in the decomposition of radicals to degradation to random scission. So as these polymer chains start degrading, they're forming different products. They're forming waxes, they're forming oils, and all of these are then continuously degraded until you end up with gases. We can see it has a very good fit with our experimental data. And this allows us to predict the material behavior and exposure to these conditions over short and long periods of time. And we'll appreciate that by utilizing the inert results here to construct what are called isothermal lifetime curves. An isothermal lifetime curve, which is shown here on the right, it's an excellent, powerful view for understanding polymer behavior under constant temperature conditions. This approach allows us to forecast degradation patterns across various timeframes, from short-term processing to long-term processing. The X represents temperature, while the Y-axis represents time. And specific temperatures and exposure times construct the curves, with each curve representing a specific percentage of degradation. In this current curve that's constructed from the virgin polypropylene in the inert environment, we're observing lower temperatures requiring more time to reach the same degradation than at high temperature, which is reasonable since temperature is our main degradation impact factor here. This predictive capability is crucial for optimizing recycling processes and developing efficient pyrolysis schemes. In the current case, by predicting how various pyrolysis conditions affect polymer degradation, we can design more efficient and targeted breakdown processes. In the context of mechanical reprocessing, applying this type of modeling to TGA data in an oxidative environment helps us inform the optimal processing conditions that minimize degradation when exposed to air. By understanding how temperature and time affect polymer degradation, we can maximize the recovery of usable material while maintaining our quality. And this is particularly valuable when dealing with recycled polymers, where previous life cycles have already impacted thermal stability. Ultimately, this isothermal lifetime prediction approach is a cornerstone for our steps in developing sustainable polymer manufacturing practices. It enables us to optimize processes, minimize waste, and improve the quality or maintain the quality of recycled materials. By understanding polymer behavior under various conditions, we're better equipped to tackle the challenges of creating these more complex processing schemes. So we now are going to be turning our focus to PCR. So again, PCR represents the materials that have completed their intended life cycle. They've been discarded, collected, and reprocessed for use. The complexity of PCR stems from that history. And unlike virgin materials or post-industrial recyclates, PCR has undergone that consumer use, disposal, and recycling process. And this journey introduces several challenges: the potential for contamination, degradation from environmental exposure, and the mixing of different polymer types. Incorporating PCR into manufacturing process requires careful consideration of the impacts on material properties. We often observe changes in molecular weight distribution, thermal stability, and mechanical properties. The economic and environmental benefits of PCR are significant. We've seen that. By reintegrating these materials into the production cycle, we reduce the reliance on virgin resources and decrease the environmental burden of plastic waste. However, balancing these benefits with maintaining product performance and safety is still an ongoing challenge. It's not just about recycling. It's about designing products with their entire life cycle in mind, including multiple recycling loops. So what we're going to do is compare 2 virgin blow molding grade HDPs against 3 commercially available blow molding grade PCR samples. And we're going to utilize these findings to determine which one would be our best alternative to displace virgin HDPE with PCR for our specific blow molding process. So we employed similar analytical techniques to compare our properties against virgin materials. We began with high temperature permeation, gel permeation chromatography to analyze the molecular weight distribution. We then performed MFI in order to compare and use as a benchmark for PCR materials. Steady shear rheometry was also applied to observe and appreciate the shear thinning behavior. Mechanical properties were evaluated through tensile testing, providing data on the tensile modulus. And these measurements are crucial for understanding how the PCR is going to perform in end use. We then employed differential scanning calorimetry to investigate thermal behavior, focusing on crystallization kinetics to model the rate and extent of crystal formation. And this particular analysis is important as crystallization behavior impacts the material properties and processing characteristics. Ultimately, this entire work contributes to the goals of increasing the use of recycled materials. So it's important to talk a little bit about blow molding. And blow molding is a manufacturing process that's used to create hollow parts like bottles. In blow molding, the polymer behavior during the parison formation, which is this particular step here, is critical. The parison is a hollow tube that forms the starting point of the process. A well-formed parison ensures even wall thickness, proper material distribution, and minimal defects. Molecular weight analysis helps predict the behavior and optimize processing. Our GPC results reveal key differences between virgin and PCR materials. Virgin samples show higher average molecular weights when compared to the PCR samples, which is expected. What is also interesting is how the polydispersity indices vary. Mostly for all of these, it's stable between 6 and 7, with our third PCR sample showing the broadest distribution. And this variability in PCR can impact processing consistency. The high molecular weights typically enhance mechanical properties, but they can increase the processing difficulty. The broader molecular weight distributions we see in some samples can actually improve the melt strength, which benefit the parison stability, which is why we observe the virgin materials have this high polydispersity index. For PCR materials, that low molecular weight could lead to reduced melt strength, and this necessitates adjustments in the processing parameters if we want to maintain product quality. While PCR, HDP, offers sustainability benefits, the variable molecular characteristics would present processing challenges that require careful management. Melt flow index here serves as a crucial benchmark for assessing flow behavior. What we're observing here is that our PCR samples fall short of meeting the industry standard MFI benchmark for blow molding. And this deviation from the benchmark has significant implications for melt strength. Lower MFI materials tend to exhibit higher melt strength, which is essential for maintaining that parison shape as discussed earlier. The PCR material fails to meet these benchmarks, so their lower melt strength may lead to parison sag or difficulties controlling a blow-up ratio during the formation of the bottle. And this can result in reduced dimensional stability and less consistent final properties. Additionally, we can also exhibit warpage in our system. So utilizing these PCR materials may necessitate adjustment of processing temperatures. These findings underscore the complexities of incorporating PCR materials into blow molding processes. Here we're showcasing our steady shear rheometry results, where we notice the lack of a Newtonian plateau in all these samples, which makes it difficult to estimate the zero shear viscosity. What we do observe is clear differences between the PCR here at the bottom and the virgin viscosity by a small magnitude change. This further validates the results of our HTGPC analysis and the MFI analysis. We notice similar shear thinning behavior for the virgin samples, which is comparable to the shear thinning behavior of PCR1 and PCR2. But PCR3 deviates from the other PCR samples, which has an increased shear thinning sensitivity. So now we're already on the lookout of what's happening with PCR3. Here from our tensile test results, we have some kind of interesting findings, in my opinion. Contrary to what I would expect, from samples with higher MFI and lower viscosity molecular weights, the PCR1 and PCR2 exhibit surprisingly high moduli comparable to the first virgin sample. Several factors could be at play here. It could be the presence of additives that could be used to enhance stiffness. The recycling process itself could induce changes in molecular structure, potentially affecting crystallinity. And it's worth noting that high quality feedstock and carefully controlled processing conditions can also contribute to these superior mechanical properties. So this underscores that importance of rigorous quality control in recycling processes. Notice how PCR3 largely fails our high-end and low-end virgin materials. So again, PCR3 has already been on our list from our results in our steady shear rheometry and from our HTGPC results. And now with our tensile results, more attention is being given to PCR3. So we turn our attention to DSC. And our DSC analysis reveals the composition and quality of our recycled materials. PCR1 and PCR2 are demonstrating thermal properties that are similar to virgin materials, particularly virgin 1. This suggests high quality feedstock and well-preserved crystalline structures, indicating that these recycled materials should process similarly to our virgin HDP. However, PCR3 represents a more complex picture. There's an extra peak that's happening here, one at 134 degrees Celsius and one at 163 degrees Celsius. And this is particularly indicative of polypropylene. So this dual peak profile points to PP contamination in the recycling stream. This contamination in PCR has significant implications for processing. It would require much more careful temperature control to ensure complete melting of both components without degrading the HDPE. We will also encounter inconsistent melt behavior, potentially leading to flow and distribution issues in the mold. Furthermore, the different crystallization rates of HDP and polypropylene in PCR could result in uneven shrinkage, warpage in the final product, and this composition can also impact the mechanical properties that we have saw, potentially reducing strength and impact resistance. So these findings underscore the importance of rigorous quality control in our recycling process. So while PCR1 and PCR2 demonstrate that the high quality recycled material closely match the virgin properties, PCR3 highlights the challenges of contamination in recycling streams. Understanding crystallization kinetics is crucial for predicting HDPE solidification during cooling. This directly impacts processing parameters and final product properties. For blow molded products, proper crystallization ensures dimensional stability and mechanical strength. We've analyzed our data using a comprehensive model that combines two key components. Here we have our conversion model, where we have two equations on the right of it. We have the Sestak-Burgert equation and the Hoffman-Lorentz equation. This model together expresses the crystallization rate as a product of these two functions, f of a, which depends on the degree of crystallization, and k of t, which is describing the kinetic dependence on temperature. So what happens is that this equation, the f of a equation, the Sestak-Burgert equation, is describing crystallization rate changes as more of the material crystallizes. And it includes parameters that indicate whether crystallization is uniform, autocatalytic, how it's affected. And on the right-hand side here, the Hoffman-Lorentz equation is describing how temperature affects the crystallization rate. It's providing insights into energy barriers that form new crystalline regions and how temperature affects the crystal growth. When we combine these two models, we can quantify the differences in crystallization behavior between the virgin and recycled materials across a range of temperatures and degrees. So this approach allows us to optimize cooling profiles and processing conditions for each material, ensuring consistent product quality. We will particularly be paying attention to the Nakamura coefficient, or the secondary nucleation constant here, as that one is indicative of the crystallization behavior. It's representing the energy required to form these fine crystals. So on the left here, we're showcasing our Nakamura coefficient values, representing the energy barrier for crystal formation. And it shows that the PCR samples generally fall within the range of the virgin materials. However, again, PCR3 is exhibiting a very high Nakamura value, indicating more significant energy requirement for initializing crystallization. And these findings have direct implications for blow molding processes. Materials with higher Nakamura values may require longer cooling times. They may need adjustments in processing parameters, particularly PCR3. And a consistent crystallization is crucial for uniform shrinkage and mechanical strength. When we're examining the relationship between modulus and Nakamura values, we're observing this logistic tendency. This suggests that there's a plateau in modulus before a significant drop in modulus occurs at higher kg values. PCR3, having the highest Nakamura value, demonstrates reduced stiffness compared to the other samples. And this is, again, likely due to that presence of contaminants that's disrupting the normal HDPE crystallization process. This unique behavior of PCR3 highlights those challenges of incorporating recycled materials with potential contaminations into our processes. Its higher nucleation energy barrier and the disrupted crystallization lead to an altered material structure and inferior mechanical properties. So these results underscore the importance of careful material selection and process optimization when we're incorporating recycled HDPE. So based on this comprehensive analysis, we've identified PCR1 as the most suitable candidate to replace version 1 in our blow molding of rigid bottles. PCR1 demonstrated thermal properties and crystallization behavior that are remarkably similar to version 1, along with comparable mechanical performance. However, it is important to note that PCR1 did have a lower molecular weight than version 1. And this is typical, again, for recycled materials. Additionally, it didn't actually meet the standard MFI benchmark for blow molding. So that means that we're going to have to change some of our processing parameters. So we're going to have to adjust our process to successfully integrate PCR1. This can include modifying temperature profiles or modifying our cycle times. Close monitoring of the melt strength and dimensional stability is crucial for the transition to this material, along with pilot tests to validate the performance under actual product conditions. PCR2 also shows a potential as an alternative, while PCR3, simply due to the contamination and divergent properties, is simply not suitable for application. Moving forward, we would need to evaluate the cost effectiveness and sustainability impact of using PCR1. This includes assessing energy consumption during processing, potential yield differences, and the overall carbon footprint reduction. So this type of approach aligns with our goal of increasing the use of recycled materials while maintaining product quality. With that, I would like to sincerely thank our partners who made this research possible. We're deeply appreciative of Netzsch for their invaluable technical support, which was crucial in our thermal analysis work. I want to also thank the Chemical Upcycling of Waste Plastics Consortium for their collaborative efforts and resources, and to the Department of Energy for their funding support. And I want to thank all of you for your attention today. Your engagement with this topic, this complex topic, but crucial topic, is greatly appreciated. And I open everything to questions and feedback. And thank you very much, guys.
Thank you. Let's take some questions from the chat window. The first question, how much of waste is polyurethane?
So when it comes to polyurethane, it is considered an other. So I personally have not seen particular numbers that correspond to polyurethane, since they're all being bundled up into others. But there has been some consistent mentions of polyurethane waste in specific feeds. Yes.
Next question. Do you know the recycling rate after 2021, after COVID impacts?
So that's actually a very interesting question. Unfortunately, due to politics, some of the data by the EPA has not been fully released after 2022. So there is some information that is missing. Yes, and it is particularly striking to try to incorporate a lot of the information nearer, instead of just relying on information from 2014, 2016, 2018, as our waste trends have definitely changed after COVID.
Next, have you recycled any other plastics using the strap recycling method?
Yes, that's a very good question. So if you can go to cup.org in order to look at a lot of the publications that we have. We've used it for polyethylene terephthalate. We've used it for polypropylene. We've used it for different grades of polyethylene. And we have different partnerships where we're trying to observe how we can further utilize this to work on mechanical recycled streams that have already been sorted, and just use strap as a sorting mechanism as well.
Next question. Can you make a recycle its content claim on a material using PIR under the FTC green guidelines?
Particularly, I'm in board with how the AU is taking care of this. The answer should be no. PIR should not count as recycled content, simply because this material has not met its life cycle. It hasn't undergone the exposure to use. It was in your factory anyway. It hasn't been outside of it. So I don't believe it would match right now. And I think that there's political push to making sure that PCR is what we're calling recycled content and not PIR.
Next question. How does the cost to recycle it compare to that of virgin materials?
It does depend. So virgin material pricing is heavily tied to the price of oil. So it's commodities. But when it comes to recycled materials, its cost is now tied to all the investment that had to be done, plus the cost of oil. It is a fact, the recycled polymers are going to cost more than virgin polymers. And for some corporations, just the brand and marketing of incorporating recycled materials into their processing streams is enough for them to eat the cost and utilize some of these recycled materials.
Next, did you have any chance to follow polymer chain entanglement disentanglement with recycling, which may affect the tensile properties?
Not particularly. That is an area that I have seen some other people in CUP start working, particularly the people who focus more on rheology, like extensional rheology, capillary rheology, and exploring some of those high stress values. So that not particularly on my end.
Next question, how did you determine what resins to use as a virgin materials in your PCR study?
So for the PCR study, this study was performed with a company. So the 2 virgin materials are their 2 virgin uses. So that's what they use in their product line. And the 3 commercially available PCR materials are 3 commercial PCR materials from their state, which they purchased and were planning on utilizing to displace their virgin material. So this is all from our partner company, and they utilize specifically what they use for their final products.
Okay, next question. Did you perform FTIR of virgin and recycled polymers?
Yes, we have performed FTIR. Some of that has been published with our CUP partners. So feel free to go to cup.org and look at some of our publications.
Next question. Did you face any challenges finding the right solvent for recycling? And how is the scalability of STRAP method?
Yes, so definitely, again, this is very good for going to cup.org and looking at some of our publications. Yes, we have developed certain techniques to determine what type of solvents to use. We have a library of solubility data. We have a computational partners that work on predicting specific solvents to target particular polymers. And when it comes to scalability, we are currently working on getting this to our pilot plant. So it's very exciting in the coming year to be able to be part of this project as we start trying to reach higher processing rates with this. But yes, definitely, cup.org. Look at our papers, please.
Next, are the PIR and PCR studies published, or will they be published?
The PIR, we're currently working on that publication, so we're working on that to get that. And the PCR one, both trying to get those January and February. The PIR is easier for me to get through because that one was mostly me. The PCR one is a collaborative effort between 5 different labs, so that one is getting there. But we're working on publishing these results. Yes.
And I believe that Alec has answered in the chat. What was the website you mentioned earlier that has recycled examples of polymer?
The website for it, for example, like cup.org, cuwp.org, where we have our publications for the CUP project.
Okay. Is it possible to determine recycled content in polymers using any techniques to prove the claims for manufacturers?
Okay, so this has been a question that it's fascinating because the answer is no. You know, when we're looking at there are some claims that certain materials after their recycled life will undergo oxygenation, and that changes their polymer structure and the polymer backbone. So you can use FTIR to kind of observe if the material has some sort of increase in the peak for the methyl group, for example. But it's too nuanced. There are particular studies that try to utilize this. We have also attempted to use this, but it's on a case-by-case basis, and I wouldn't generalize and say like, oh, there's this one method that just works. In reality, that is a big challenge right now, is how do we identify these claims about including post-consumer recycled material in these products?
And it probably ties into this question. Have you had any success in determining the amount of recycled material in a given sample? If so, how?
No, we have not had success. Particularly myself, I have not had success in determining with the methods that I'm utilizing. Yes, you can observe changes in viscosity. Yes, you can observe some changes in the DSC behavior. But when you start, you don't just do a test once. you do a test multiple times over and over. When you start averaging your results, they're comparable. Particularly, there is interest in using FTIR in order to observe this, but this is an ongoing challenge.
Next question, do you use Hansen's solubility parameter to choose the solvent?
That is correct.
Okay. Next, in your experience, is it better to use 100% recycled material or blend with virgin material? I have seen arguments for both. What are the pros and cons?
Yes, so the arguments for both are particularly interesting. When you start blending with your virgin material, you are bound, this is just a simple mixing rule. You're bound to achieve properties closer to your virgin material. There is the 70-30 rule, where you utilize 70% virgin material and 30% recycled material, allowing you to essentially maintain the properties of the virgin material. The problem, the con is, if you don't have good quality recyclate, you can just start introducing contaminants that may negatively affect the processing of material, and may even affect how your material is going to be approved regulatorily. There are some companies that have pushed towards 50% recyclate, even 70% recyclate, when they have really good high quality feedstock. When it comes to 100% recyclate, that's sort of what the PIR study was attempting to demonstrate. It's like, hey, you can maintain your properties of the material, even though you are losing some of your molecular weight, you are changing your flow properties, but you are maintaining your mechanical properties. So as long as you're carefully processing your material, as long as you have a high quality recyclate, there is a consideration for using 100% recycled material. But yeah, it is definitely a case-by-case basis, and it is very difficult to generalize for this topic.